So in this particular session, I'll be covering about the greedy approach, specifically about the minimum cost spanning trees, which includes the Prim's algorithm and as well as the Kruskals algorithm. So far we have covered about what is the spanning tree and what is the minimum cost spanning tree and what are the various kinds of the algorithms related to the minimum cost spanning tree. Coming to the spanning tree, how we can define a spanning tree is a subset of the graph G such that all the vertices are connected using the minimum possible number of the edges and which does not form any kind of the cycles. That is, like for example, let the graph G equal to V comma E. Let the graph equal to G equal to V comma E, where V indicates the set of the vertices and E indicates the edges, be an undirected connected graph. A subgraph T equal to V comma E dash of the graph G is a spanning tree of the G if and only if that particular subgraph that is formed is a particular tree. So a greedy method to obtain a minimum cost spanning tree builds this edge. That is, when you consider about the two algorithms, we have the Prim's algorithm and the Kruskals algorithm. So coming to the definition of the minimum cost spanning tree, that is a minimum spanning tree, or which can also be said as minimum cost spanning tree, is a subset of the edges of a connected edge weighted undirected graph that connects all the vertices together without any cycles and with the minimum possible total edge weight. That is, here if you consider the spanning tree, that is what is this actually the spanning tree, consider A and the B and as well as C and the D kind of the given graph. Then one of the possible solution for the spanning tree is, that is, from A we can reach to B, and from B we can reach to C, and from C we can reach to D. This is one of the possible spanning tree. And as I mentioned in your previous video, that is in order to find how many number of spanning trees that can be generated, that is n to the power of n minus 2. So if you consider n equal to 4, that is 4 vertices. That is 4 to the power of 4 minus 2, that is 4 square. 16 such spanning trees can be generated. And if you consider the another kind of the spanning tree, that is like take for example from A we can reach to D, and from D we can reach to C, and from C we can reach to B. So consider the edge cost which is been associated within your undirected graph to be equal to something like your 2, 4, 1, 6, 5 and similarly 8. So between the spanning tree 1 and similarly the spanning tree 2, which is the minimum, that will be the solution for the minimum cost spanning tree. And similarly, there are two ways where we can solve the problem of the minimum cost spanning tree, that is Prim's algorithm and as well as the Kruskals algorithm. So coming to the Prim's algorithm, that is algorithm Prim E comma cost comma n comma t, that is T indicates a spanning tree where E indicates the edge, cost adjacency matrix, n indicates the number of the vertices. And if you consider this kind of the greedy method to solve the minimum cost spanning tree using the Prim's algorithm, that is here a greedy method to obtain a minimum cost spanning tree builds the tree edge by edge. The next edge to include is chosen according to some kind of the optimization criterion. That is, if you consider the graph, that is from A we can reach to B, and from B we can reach to C, and say C to D, and similarly like B to E, and as well as D to E, and there is also edge from B to D, as well as consider the edge from E to C. So here the steps that has been involved to find the minimum cost spanning tree using the Prim's algorithm is, you will be choosing certain kind of the optimization criteria, which involves the greedy method. That is, the simplest such criteria is to choose an edge that results in a minimum increase in the sum of the cost of the edges that is been included so far. That is, here if you have a to b to be equal to 2 and a to c to be equal to something like your 4, from a, what is the minimum edge cost, the lowest edge cost that has been associated to the other paths that are been available. That is, from a we can reach to b and from a we can reach to c. Between these two, what is the minimum? The minimum is equal to 2. And you have to consider that kind of the edge. So there are two possible ways to interpret this kind of the criteria. That is, in the first, the set of the edges so far selected form a tree, and thus if A is the set of the edges selected so far, then A forms a tree. The next edge u comma b to be included in A is the minimum cost edge, which is not present in A. That is nothing but the remaining vertices. That is, already we have considered A comma b, and what are the remaining edges that are being present. And out of all these kinds of the edges, which is the minimum. So here, if you consider the various kinds of the steps that are being involved in the Prim's algorithm, that is k comma l be an edge of the minimum cost in the E, that is in the set of the edges, and minimum cost equal to cost of k comma l, the edges that you have considered. That is, like, for example, k is an A vertex, and similarly L is the next vertex with the minimum edge, that is A to B, with the cost to be equal to 2. And here we are considering the tree to be equal to from 1 to 2. That is 1 to 1, where we are giving with some kind of the variable to be equal to k, and t of 1 to 2 with the variable to be equal to L. And similarly, you'll be selecting the next edges in such a way that what are the remaining edges which are not being considered from the previous step, and from the current vertex, what are the various paths which are been available to reach to the other kind of the vertices. Out of all these, what is the minimum? And such kind of the vertex or the edge has to be taken into the solution set. In this particular fashion, you'll be finding out the minimum cost spanning tree for this kind of the Prim's algorithm. And as a part of the example, that is given certain kind of the undirected weighted graph, that is from 1 to 2 with the edge cost to be equal to 4, and similarly 1 to 3 with the edge cost to be equal to 5, and so on. So how this kind of the graph problem can be solved using the minimum cost of spanning tree with the method that is Prim's algorithm. That is, from consider some kind of the source vertex, that is source vertex to be equal to 1. So from 1, what are the various paths which are been available? That is, from 1 we can reach to 2 with the cost to be equal to 4, and similarly from 1 we can reach to 3 with the edge cost to be equal to 5. Of course, you should also take into consideration of what are the various vertices that are being present in the given graph, that is 1, 2, 3, 4, and similarly 5. So here between these two, that is 1 to 2 with the edge cost 4, 1 to 3 with the edge cost 5, what is the minimum? The minimum is equal to 4. So from 1, the next step that has to be considered is from 1 we can reach to 2 with the edge cost to be equal to 4. So here vertex 1 is been explored, vertex 2 is also been explored. And the next case, that is 1 to 2, we can strike it off this one because we have already taken this into the solution set. The remaining edge that is not yet been considered is 1 to 3 with the edge cost to be equal to 5. So from the current vertex, that is from 2, what are the edges that are being connected to? So from 2, we can reach to 4 with the edge cost to be equal to 2. And from the previous step, that is 1 to 3 with the edge cost 5, and from the current vertex, that is 2 to 4 with the edge cost to be equal to 2. What is the minimum? The minimum equal to 2 to 4 with the edge cost to be equal to 2. So take that into the consideration for your solution set. So from 2, we can reach to 4 with the edge cost to be equal to 2. So here we have taken the vertex 4 into the solution set. So already we have included 2 to 4, and that is the purpose where I am erasing this one. And from the current vertex, That is, the current vertex is nothing but it is 4. So from 4, what are the various edges which are being connected to the respective vertices? That is, from 4 we can reach to 3 with the edge cost to be equal to 6. From 4 we can reach to 5 with the edge cost to be equal to 3. So 4 to 3 and similarly 4 to 5. We cannot consider 4 to 2 because vertex 2 is already explored. And that is the purpose where we cannot take into the consideration of 2 into the solution set. It is a duplication. So here out of these 3, that is with the edge cost 5, 6 and similarly 3, the minimum will be equal to 3. So take this into the solution set. That is, from 4 we can reach to 5 with the cost to be equal to 3. So we can discard this one, and the remaining vertices that are being present are 1 to 3, the edges. That is 1 to 3 with the edge cost 5, 4 to 3 with the edge cost to be equal to 6. And similarly, you can also strike off this 5 because vertex 5 is also being taken into the consideration, into the solution. And similarly, from the current vertex, that is from 5, where can we reach? So from 5, we can reach to vertex 3 with the edge cost to be equal to 1. And there is only one edge that has been connected so far. So here, if you consider the edge cost to be equal to 5, 6 and similarly 1, what is the lowest or the minimum? The minimum will be equal to, with the edge cost to be equal to 1. So take that into the solution set. That is, from 5, we can reach to 3 with the edge cost to be equal to 1. And so we can strike off this vertex 3. Do we have any other another unexplored vertices? We have covered all these kinds of the vertices, and that is how we can say this is the solution for your minimum cost spanning tree. What is the cost? So cost equal to 4 plus 2 plus 3 plus 1, 4, 5, 6 plus 4, that will be equal to 10. So this is the minimum cost spanning tree. That is, from 1 to 2 and similarly 2 to 3 and similarly 4 to 5 and as well as 5 to 3 with the edge cost to be, with the total cost to be equal to 10. This is the minimum cost spanning tree, which can be solved using the Prim's algorithm. So source vertex that you have considered is 1, and similarly the other possible solution, that is here we have the 1 comma 2 with the edge cost to be equal to 4. Similarly, the same thing which I have said, 1 comma 3 with the edge cost to be equal to 5. Between these two, the minimum is 1 to with the edge cost 4. From the previous explored vertices, that is 1 to 3 with the edge cost 5, and similarly 2 to 4 with the cost to be equal to 2. And between these two, the minimum is 2 comma 4 with the edge cost to be equal to 2. In this particular fashion, we'll be exploring the various kinds of the other vertices which are yet to be explored. And out of this one, what is the minimum? The minimum will be equal to, that is 4 comma 5 with the cost to be equal to 3. So take that into the solution set. And similarly, the remaining edge costs and as well as from the current vertex, what can we reach? That is 5 to 3 with the cost to be equal to 1. And that is so we can say the minimum is equal to 1 and the edge is 5 to 3. So edge 5 to 3 has to be taken into the solution set. And that is how we can get the final spanning tree, which is the minimum cost spanning tree. This can be said using the Prim's algorithm. And the same thing can also be solved using the given graph. That is how to solve using the Prim's algorithm. That is, from 0. What are the various vertices that are being present? That is 0, 1, 2, 3, 4, 5, 6, 7, and similarly 8. These are the vertices which are present within the graph. And similarly, start from your source vertex, that is 0. So from 0, we can reach to 1 with the cost to be equal to 4. From 0, we can reach to 7 with the cost to be equal to 8. Between these two, what is the minimum? The minimum is equal to that is 4. So 0 to 4 with the edge cost to be equal to 4 has to be taken into the solution. That is vertex 0 and similarly vertex 4 are taken into the solution. And the next thing, you can strike off this 0 to 1 because we have taken into the solution, and from the current vertex, that is from 1. So from 1 we can reach to 2 with the edge cost 8, and from 1 we can reach to 7 with the cost to be equal to 11. And out of these, what is the minimum? So minimum is equal to, here we can consider there are two minimums, that is 0 to 7 with the edge cost to be equal to 8, and 1 to 2 with the cost to be equal to 8. So you may get two different solutions, but ultimately at the last you'll be having the same kind of the final total minimum weight. That is in the other solution, that is 0 to 4 0 to 1 with the edge cost to be equal to 4. And one of the possible ways, solution 1, that is 1 to 2 we can connect with the edge cost to be equal to 8. And in the other solution, you can also take 0 to 7 with the edge cost to be equal to 8. So consider this kind of the solution, and then we can expand. That is, we have taken 1 to 2. This is your respective minimum edge cost. So here we have taken the 2 into the solution set, and we can erase this 1 to 2 with the edge cost 8. And from 2, what are the various edges which are been connected to? So from 2, we can connect to 8 vertex with the cost to be equal to 2. From 2, we can connect to 3 with the cost to be equal to 7. From 2, we can connect to 5 with the cost to be equal to 4. Out of these, what is the minimum edge cost? So the minimum edge cost that has been associated is 2. That is 2 to 8 with the edge cost to be equal to 2. So from 2, we can reach to 8 with the cost to be equal to 2. So 8 is been covered. And in this particular fashion, go on finding what is the minimum edge cost that has been associated among the various kinds of the subgraphs which are being present. So if you solve this kind of the problem, as I mentioned, there are two solutions. The first solution, that is 0 to 1 with the edge cost to be equal to 4, 0 to 7, 8, 2 to 8, and so on. So here you can observe there are no cycles which are being formed. The other solution where I have taken, like take for example, so 0 to 1 with 4 cost, with the cost to be equal to 4, and similarly 1 to 2 with the edge cost to be equal to 8. And the other solution, 0 to 1 with the edge cost 4, 0 to 7 with the edge cost to be equal to 8, because we have obtained two minimum costs, out of which you can select either of this one, and ultimately in both these solutions the cost will be the same, the minimum cost will be the same. So what is the minimum cost? If you sum up the minimum edge cost which are being associated, that is, here you can observe the minimum cost equal to either you take solution 1 or solution 2. Consider this is your solution 1 and this is your solution 2. So either you take solution 1 or the solution 2, you get the minimum cost with the cost to be equal to, that is 37. So this is how we can solve the problem of the minimum cost spanning tree for any kind of the undirected weighted graph. And coming to the Kruskals algorithm, so here the Kruskals algorithm, you need to construct the heaps, that is minimum heap. According to this kind of the algorithm, that is E cost comma n comma t, that is edge cost adjacency matrix, and similarly n indicates the number of vertices, so on, and where is the E is the set of the edges within the graph, and out of the t, what does this t indicates? T is a set of the edges in the minimum cost spanning tree. And at the last, you can observe the return minimum cost. Whatever the minimum cost that is been associated for the given undirected weighted graph, the cost will be returned. So here we will be using about the heapify function. If you recall about the heap sort, within the case of the heap sort, we'll be using the heapify. The same concept is also been implemented to find out what is the minimum kind of the edge that has been associated. So for I equal to 1 to n, do the parent of I equal to -1 we have initialized, and for each kind of the vertex which may contain the different kind of the sets, assign the value of your I to be equal to 0, minimum cost equal to 0. And there are certain steps which are being associated to simplify your entire algorithm related to the Kruskals. We can explain. So basically, the Prim's algorithm takes the time complexity of big O of n square, and whereas the Kruskals algorithm takes big O of e log e time complexity. So as a part of the example related to the Kruskals algorithm, given certain kind of the weighted undirected graph, here you can observe from A there are some 1, 2, 3, 4, 5, that is n equal to 5. The total number of vertices that are present are 5, and the vertices are A, B, C, D, E. These are the vertices. And how to solve the problem of the minimum cost spanning tree using the Kruskals algorithm? That is, keep the edge sets in the ascending order. What does it mean? That is, here we have from A. So from A, we can reach to B with the edge cost to be equal to 1. From A, we can reach to E with the edge cost to be equal to 5. From A, we can reach to C with the edge cost to be equal to 7, and similarly, and so on. So B to C with the cost 3, C to D with the cost 4, A to D with the cost to be equal to 10, and D to E with the cost to be equal to 2. So how many edges are there? 1, 2, 3, 4, 5, 6, 7. So 1, 2, 3, 4, 5, 6, 7. So 7 edges are being indicated according to the edge cost. And the next step that is to be done is you have to sort in the ascending order. That is here, which is the minimum? The minimum is 1. So A to B with the edge cost to be equal to 1, and find out what is the next minimum edge cost. The next minimum edge cost is 2, and that is D to E with the cost to be equal to 2, and so, go on for the next minimum edge, that is B to C with the cost to be equal to 3, and similarly C to D with the cost to be equal to 4, and A to E with the cost to be equal to 5, and the next minimum is, that is A to C with the cost to be equal to 7, and the next list is A to D with the cost to be equal to 10, and connect these kinds of the edges. That is, from A we can reach to B with the cost to be equal to 1. So we have taken into the consideration of A vertex A and similarly vertex B. And similarly, the next edge minimum edge cost is equal to 2. That is D to E. So D to E with the edge cost to be equal to 2. And the next minimum edge cost here you need to strike off D and as well as E. And the next minimum edge cost is B to C. So B to C with the edge cost to be equal to 3. So while connecting these kinds of the edges, make sure that it should not form the cycle, because the concept of the spanning tree itself indicates it should not form any kind of the cycles. So whenever you are connecting these kinds of the edges, if it does not form any kind of the cycle, then you can take that kind of the edge into the solution set. If it forms the cycle, then you should discard that kind of the edge and go for the next edge that is to be taken. So according to this case, so far we have not formed any kind of these cycles. So B to C with the edge cost to be equal to, that is 3. And similarly C to D, C to D with the edge cost to be equal to 4. C to D with the edge cost to be equal to 4. And can I draw from A to E? That is, if I draw from A to E, it forms a cycle. This is a cycle that has been formed, and that is the purpose where we cannot connect this kind of here the edge. And moreover, you can also observe C is also been, vertex is also been taken into the solution, and that is how we can stop. So what is the total cost? That is here A to B, that is 1 plus 3 plus 4 plus 2, that is 3 plus 1, 4, 4, 8, that will be equal to 10. So this is how we can solve the problem of minimum cost of spanning tree using the Kruskals. So if you recall, given certain kind of here the edge, directly include, and the next is rearrange these kinds of here the edges according to their cost in the ascending order, and you'll get this kind of here the edges, and connect the edges in such a way that it should not form any kind of here the cycles. That is how we can solve the problem of the Kruskals, the minimum cost of spanning tree using the Kruskals algorithm. So the same thing you can observe, that is here edge and similarly weight. That is A to E with the edge cost to be equal to 5, and similarly A to D with the edge cost to be equal to 10. I'm denoting all the kinds of here the edges which are being connected. That is A to C with the edge cost 7, and similarly A to B with the edge cost 1, B to C 3, and similarly C to D 4, and D to E with the edge cost to be equal to 2. And I'm rearranging these kinds of here the edges based upon the cost in the increase in the ascending order. That is A to B 1. This is your first edge that has to be taken, and the next edge, that is D to E with the edge cost to be equal to. What happens if you have the same edges? Like for example, here you have 2, and the next one here also, if you consider the 2, then you should also take B to B comma C into this kind of here the order. So the next minimum will be equal to B to C with the edge cost to be equal to 3, and so on. So rearrange these kinds of here the edges according to the increasing order. And the next step is connect these kinds of here the edges. That is A to B, there is an edge that has to be connected. And similarly, the next minimum is D to E. That is, here we have finished about A to B. This is in your sorted fashion. And the next one is D to E 2, and the next one, that is B to C. So while connecting this kind of here the B to C, make sure, or any kind of here the edges, make sure that it does not form any kind of here the cycles. So D to B to C, and the next minimum will be equal to C to D, and with the cost to be equal to 4. And we cannot connect from A to E because the cycle will be formed. We cannot connect from A to C because if you draw this A to C, a cycle will be formed. And moreover, all the edges, all the vertices, so A, B, C, D, E, all the vertices are present within this kind of here the spanning tree, and that is how we can stop this one. And the total cost, that is sum of all these kinds of here the edge cost, that is 1 plus 1 plus 2 plus 3 plus 4, that will be equal to, that is 10. And this method we can solve the problem of the Kruskals. So coming to the next example, that is the solving the Kruskals algorithm for the given undirected graph, how we can solve. So here, as I mentioned, what are the total number of the vertices which are being present? That is A, B, C, D, E, and then F. These are the vertices which are present. And out of this, if you consider what is the minimum, that is B to D is the edge with the minimum. That is, draw the edge from B to D with the edge to be, with the edge cost to be equal to 1, and find out what is the next minimum edge cost. the next minimum edge cost is equal to 2. So from D, we can reach to C with the edge cost to be equal to 2. So far we have covered B vertex and similarly D vertex, and now C vertex has also been covered into the solution set. And the next minimum edge is 3. So while connecting this kind of the edge, make sure that it should not form any kind of the cycle. So here from B, we can connect to A with the edge cost to be equal to, that is 3. And the next edge that has to be taken is 4. So from A, we can reach to E with the cost to be equal to 4. Find out what is the next minimum. There are two minimums, that is 6 and as well as 6. You can take, like take for example, if you connect from A to C, if you connect A to C, a cycle has been formed. What is a cycle? That is, this is your respective cycle that will be formed, and that is the purpose where you cannot take that kind of the edge into the solution set. So what is the next edge that has to be associated? That is E to F. That is from E, we can reach to F with the edge cost to be equal to 6. So far we have covered E and as well as F. And this is the minimum cost spanning tree with the cost to be equal to 2 plus 1, 3, plus 3, 6, plus 4, 10, plus 6. That is 16 is the minimum cost spanning tree. That is here, this is a given input edges. And similarly, rearrange this kind of the edge based upon the cost. That is here, you can observe the respective edge which are being arranged according to the order, and take that kind of the edge into the solution set, whichever is the minimum. And this is how you can solve the undirected graph to form the minimum cost spanning tree. And what is the cost that has been associated? The cost that has been associated is equal to, that is 2 plus 1, 3, plus 3, 6, plus 4, 10, plus 6. That will be equal to 16. So far the same thing is been discussed. Now consider another example where you need to solve the same thing using the like for example Prim's algorithm, and now consider about the solution using the Kruskals algorithm. So when I say about the Prim's algorithm, then from take the some kind of the initial vertex, you can take 1 or 5, any kind of the source vertex. So consider from 1, from the source vertex to be equal to 1. So from 1 we can reach to 4 with the cost to be equal to 1, and from 1 we can reach to 5 with the edge cost to be equal to 4, and from 1 we can reach to 2 with the edge cost to be equal to 2. What is the minimum? The minimum is 1. We can reach to 4 vertex with the edge cost to be equal to 1. So from 4, what are the various edges that are being connected? So from 4 we can reach to 5 with the edge cost to be equal to 9, 4 to 3, 5, and similarly 4 to 2 with the cost to be equal to 3. And the remaining, what is the remaining thing? That is from 1 we can reach to 2 with the edge cost to be equal to 2. So take that into the solutions. And this is how you'll be solving the problem of the Kruskals algorithm. And coming to the, Prim's algorithm. And when coming to the Kruskals algorithm, so when coming to the Kruskals algorithm, then what is the minimum out of the various kinds of the edges that are being connected? That is this is your minimum edge cost. That is from 1 we can reach to 4 with the cost to be equal to 1. Find out what is the next minimum. That is 2. So from 1 we can reach to 2 with the cost to be equal to 2. Similarly, what is the next minimum? The next minimum, it can be either 3 or it can be either this kind of the edge. If I draw from 2 to 4 within your this kind of the tree, then cycle will be formed, and that is how we cannot take this into the solution. So the next one is 2 to 3 with the cost to be equal to 3. And what is the next minimum? That is 4 is your next minimum. So 4 is the next minimum that has to be taken. And what is the, does it form any kind of this cycle? By connecting 1 and 5, it does not form the cycle. So you can take this into the solution. And what are the remaining vertices which are being left out? That is, here we have the 6 vertex. And what is the next after 4? That is 5. So if I connect from 4 to 3, a cycle will be formed. And that is why we cannot take this into the solution set. And what is the next minimum? That is 7 will be the next minimum. That is 2 to 6. So we can connect. That is 2 to 6 with the edge cost to be equal to 7. And have we finished all the vertices? We have finished all the vertices. That is 1, 2, 3, 4, 5, 6. And the minimum, what is the cost? That is 4 plus 1, 5, 6, 7, 14 plus 3, that will be equal to 17. So this is the minimum cost spanning tree which can be solved using the Kruskals algorithm. So the same thing, 4 plus 1, 5, 6, 7, 14 plus 3, that will be equal to 17. So, this has been left as an exercise which you can solve by yourself. Solve the problem of minimum cost spanning tree problem by using the Prim's algorithm and by using the Kruskals algorithm. And in your next video, I'll be covering about the single source shortest path, which can also be solved using the greedy method.